Okay, greetings. This is the beginning of chapter 12 notes. We'll see how far we get. Um, this is systems of linear equations. So, systems of equations and equalities is chapter 12. So, here we go. All right, so just some terminology in the beginning. And what I've tried to do is I've tried to match this up with some material, of course, on Blackboard to give you plenty of opportunity to see examples and fully worked out solutions. Um, we'll see how that goes. I did post up a problem set take home, which is due approximately in a week. And just please remember that I really don't want to take these things late. Um, Most people get everything in on time, and I mean, a little while after the deadline's not a big deal, but some people have taken advantage of that. I just have to, unfortunately, I just have to put an end to that. So I'm not going to take things late. So it's 6 p.m. on whatever date is indicated, and that's the way it has to be. All right, and what I'm continuing to do is don't forget we had two exams in class prior to the recess and this coronavirus pandemic. And exam number 3 is composed of the material from chapter 10, which I think was polar and was vectors and things of that nature. And exam number 4, which most of you should be finishing up at this point, had the let's see, it was the parabola, the ellipse, the hyperbola, rotation of axes, and parametrics. That was all chapter 11. So those 5 problem set take-homes will compose exam number 4. And what we're doing here now is chapter 12, and depending how far we get, I'm probably going to combine chapter 12 with some of the later stuff. We'll end up with 5 exams. And I will, since I'm not going to give a final exam, I will take those 5 exams and I will drop the lowest grade. So that's how that should work. Okay. And, try and be as fair as I can. These are difficult times, but, you know, we'll see what we can do. Okay, so chapter 12, section 1 and 2, I'll try and at least touch on section 2 today, talks about systems of linear equations. So here we go. And all of this should be on Blackboard. You can download it, print it out, and have a copy handy as you're going through this. All right, so here we go. 2 equations, 2 unknowns, linear, meaning there will be lines, looks like this, where the a's, b's, and c's are coefficients. Okay? And these basically would give us 2 lines. We'll talk about a geometric aspect of this later on. And 3 equations, 3 unknowns. X, Y, and Z would be the variables, and the A, B, C's, and D's would be the coefficients, the constants, and these would talk about 3 planes. Okay? So, solution of any system of linear equations is the set of points in common to each of the lines or planes. The solutions could be, all right, we're specifically talking about this case here, 2 equations, 2 unknowns. What could the solutions be? They could be a single point, or if we're talking about 3 planes here, we could be talking about an ordered triple. So it's an ordered pair if we're talking about lines, an ordered triple, 3 space if we're talking about intersectional planes. You could also get an infinite number of points as the common solution, which could mean a line or a plane, or we could have no common solution, which is symbolized by the empty set. Okay, so let us take a look at then geometric interpretations of these. All right, so there are 3 things that could happen if we're dealing with 2 equations, 2 unknowns. We could have the 2 lines cross in a single point. A single point is our solution, and that's called a consistent system of equations. So if you hear that term, this is what they're talking about, that phrase rather. Okay, we could have no points of intersection. The only way that that could be is if the lines are parallel. No solutions, that's called an inconsistent system of equations. Or we could have an infinite number of solutions, and solutions are common points now, right? We have an infinite number of points of intersection, the lines would coincide. This is called a dependent system of equations. So that would be what happens in two dimensions if we're talking about lines. We could have something similar. I shouldn't say similar, I should really say analogous happen. System of three equations, three unknowns. Now, what I'm showing you here is incomplete. There are lots of possibilities, so let's just take a look. Okay, now when we talk about points of intersection, we're talking about points of intersection common to each of the three planes. Don't forget, if you have ax plus by plus c equals d, you have three unknowns, x, y, z, that would map out or graph out to a plane or a flat surface in three dimensions. So it could be that you have no points of intersection common to all three planes. You see, you have a situation here where the planes are like are parallel, never touching, no points in common. Or you could have this type of situation where you have two of the planes have a line in common, the other two have another line in common, but there are no points of intersection common to all three. So this would be a situation visually, geometrically, where we'd say we have no solution. Now, it could be you have exactly one point of intersection is common to all three planes. That would be the point right in there, okay? All three planes go through that one single point. So a single unique solution would mean a single common point. So this is, what we typically are shooting for, but it doesn't always happen. Okay, now it could be that, and as I said, these relationships are not all the things that could possibly happen. I'm just showing you some of the things. There are other pictures in your textbook. You could have you have an infinite number of points in common, which in this case is a line that you can see all three planes intersect in, so that's possible as well. So many other relationships are possible but not shown. All right, just to give you an idea. Okay, there's a certain amount of terminology that we have to go through, and chapter 12, section 1 deals with this, so I'm going to deal with this. For a unique solution to a system of equations to exist, this is important. It's necessary but not sufficient that the number of unknowns or variables be the same as the number of equations. So it's necessary for two equations to have two equations and two unknowns, but that's not enough. It's necessary to have a unique solution if you have three equations, three unknowns, but that may not be enough. Now let's do some examples so we understand the meanings of the word necessary and sufficient. In mathematics, like in life, they have specific meanings. Life example, you want to sew a torn garment, a needle is necessary but not sufficient because you also need thread. Thread is necessary but not alone. It's not sufficient without a needle. Together, both a needle and thread are both necessary and sufficient to sew a torn garment. Okay, so give you an idea of what we're talking about here. Just because you have two equations, two unknowns, doesn't mean you're always going to have a unique solution. Just because you have three equations and three unknowns, it doesn't mean that you're going to have a unique solution. They're necessary, but they may not be enough, okay? Okay, so I have a couple of examples here. Examples without a unique solution. And the reason, in this case, the necessary condition is not satisfied. Examples, beginning with two equations, two unknowns. Okay, here are two equations, but it turns out they're really the same thing. You really have one equation, two unknowns. So just having two equations is not sufficient. It's necessary, it's needed, but not enough. So equivalent to one equation, two unknowns, the lines are coincident, infinite number of solutions. Okay, example 2. The necessary condition is satisfied, meaning two equations, two unknowns but still not sufficient, meaning not enough, since the equations are contradictory. In other words, if you take this equation, you multiply it by -2, you would see you get these equations, and they contradict one another. I mean, how can -4x plus 10y be equal to 3 and at the same time be equal to -6? Can't happen. So this is equivalent to two inconsistent equations, lines are parallel, no solutions. So another example, let's do an example with three equations, three unknowns. Okay, here, three equations, three unknowns. You got 1, 2, 3 equations, x, y, z, three unknowns. And what happens again is the first two equations really are contradictory. Okay, so no solutions. Here's a situation where it turns out that, let's see, how does that work? Well, let's see. If you add the second and third equations, you get x plus y equals 9 because the z's cancel. So you really only have, in this case, one equation and two unknowns. So, I mean, crazy things happen. So let's go back. Here's the idea. It's necessary, but not enough, not sufficient number of unknowns be the same as the number of equations. Okay, so that's the idea. And okay, so that is going to end our first little bit of an introduction. So let's look at some examples. Okay, examples are always good. So let's see, what do I want to look at? Okay, here we go. Let's look at, that's not quite what I want yet. Okay, let's look at an example here. Now, I would think in high school, Algebra 1 at least, you covered how to solve systems of equations. You probably did examples by graphing, and then you probably did examples by adding and subtraction, and you did examples by substitution. So the last two are called algebraic methods. So what we're going to do is I put this up. This is on Blackboard. This is an example of solving a 3 by 3 algebraically. Okay, and we're going to learn some other methods. We'll learn matrices and Cramer's rule, but right now, let's just do a little bit of review. This should be mostly review, solving a system of equations algebraically. So this is called a 3 by 3 system. 3 equations, 3 unknowns. And instructions say show all work, show checks, attach no additional sheets. So this is on Blackboard, and the solutions I'm showing you here are completely on Blackboard. Okay, so first off, there are lots of different ways to do these. No two students are going to probably come up with the same exact solution. You'll come up with the same answer, but you're not going to come up with the same method. And it's important not to panic about this, okay? So I'm giving you a plan. Whoops. What I'm going to do, and this is not the only way, but this is a way. I'm going to work to eliminate the z. Now, you could work to eliminate the x, you could work to eliminate the y. Those are different approaches. I'm going to, in this example, plan to eliminate the z. So let's talk about how I do that. All right, if you're looking at what I'm going to do is I'm going to use equation A. I'm going to multiply it by 3, which will give me a 3z here, and I'm going to add it to equation 3 or equation C. I think I labeled them A, B, C. Okay, so here's my plan. And it's a good idea to sort of label things if you can to keep your head straight about what's going on. So if these equations are called A, B, C, I'm going to take equation A and multiply it by 2, right? Look at that 2 out there. So I get 6x minus 4y plus 2z is 24. So this is 2a, and I'm going to add it to equation B. Because if I write equation B under that, here's what I'm going to notice. I have a 2z here, a negative 2z there, so I'm using addition and subtraction. So if I add these equations term by term, in order to do that, everything has to be lined up. Got to have a column for the x's, a column for the y, a column for the z's, a column for the constants, and the equal signs have to be lined up, right? So if I add these, the z's are going to cancel out. 24 and negative 9 is a 15. 6x and 1x is 7x. Negative 4y and 3y is negative 1y. So I get this, which I'm calling equation D, just in x's and y's. What I'm now going to do is I'm going to try and eliminate the z in equation C by the same method. Now in this case I have a 1z, equation A, and negative 3z here, so I'm going to multiply this guy, equation A, by 3. So 3 times A and multiplying is 9x minus 6y plus 3z equals 36. Multiplying everything by 3. And equation C I'm just going to write down. And notice how I've labeled things so I can follow it, so you can follow what I'm doing. Okay? Okay, so what we get then is here's equation C. I'm going to add these like terms, and notice everything is lined up, very important. 36 negative 4 is 32. The z's cancel. I get negative 10y and 11x. So now look at what I've got. Okay, I've gone from 3 equations and 3 unknowns to 2 equations and the same 2 unknowns. So I'm reducing step by step the level of difficulty. Let me say that again. I've gone from 3 equations and 3 unknowns to equations D and E, which are 2 equations and 2 unknowns. The same 2 unknowns, of course, x and y. So now what I'm going to do is I'm going to look at these 2 equations, and I'm going to plan to eliminate one of the variables, and that will bring me down to 1 equation and 1 unknown. Okay, so arbitrary, I decide my plan, I'm writing down the plan so we all can follow it, to eliminate the y. So that means I want to make the number of y's here the same as the number of y's here. Now, most of us are not good with subtracting assigned numbers. So if this is a negative 10y, I would rather make this a positive 10y. So if you have that little fear of signed numbers and subtractions, that's why I'm multiplying equation D by negative 10. Now, notice I've labeled things so I can keep track. D is this equation. E is this equation. I've boxed them in so I can follow this. Don't make the old man, that would be me, when you hand in work like this, have to strain and tell what you're doing, because if I can't figure it out, it's wrong. Okay, so I'm taking equation D, multiplying it by negative 10. So I get negative 70x, positive 10y, and negative 10 times this, negative 150. I'm then going to take equation E and just write it down. That's why that's just an E. And now look at what I've got here. The y terms have the same coefficient, so when I add, they're going to cancel. So I add up these guys, and again, notice everything is lined up. The x's, the y's, even the equals, that's important, and the constants. So negative 150 and 32 is negative 118. Use a calculator if necessary. These guys cancel, which is what we want. And negative 70 positive 11 is negative 59x. Now I've got 1 equation and 1 unknown I can easily solve. So x is positive 2. I'm boxing it in because I'm proud of my result. And by the way, you can get fractional answers, but I'm not going to torture you. I'm going to give you problems that work out reasonably. Okay, so please, if you get a fractional answer, then you go back and check your work. Check your arithmetic, check your signs. Okay, so let's do a quick review. We started with 3 equations and 3 unknowns. By eliminating the z and 2 of them, we ended up with 2 equations and 2 unknowns. So we went from a 3 by 3 to a 2 by 2, and then we worked with this pair of equations to eliminate the y. We could have eliminated the x, of course, but I had a plan to eliminate the y. Notice I wrote the plan down so you can follow it, so I can follow it. And we ended up with x equals 2. Okay, now that you've got x equals 2, you work backwards. You pick an equation that has an x in it, and you get the other variable y. You wouldn't want to plug in back to here because then you wouldn't know, the y or the z. So you want to go back to where there's y and one other variable. So look at what I'm doing. I'm telling you exactly what I'm doing. I'm substituting x equals 2 into d. That keeps my head straight about what I'm doing. So I write down d. In place of x, I put a 2. I'm going to solve this. I subtract 14 from both sides, so I get negative y is 1, so y is negative 1. I now have both x and y. So at this point, I'm going to substitute into one of my original 3. It doesn't matter which one. Just keep your head straight and, say what you're doing. All right, so I'm going to substitute x equals 2 and y equals 1 into a. Okay, so this is a, B, C. So, you got to keep your head straight so you can follow it. So I write down equation A. I plug in x is 2, y is negative 1. I work this out. This is 6. This is positive 2. 6 and 2 is 8. 8 plus z is 12. Z is 4. And if you're smart, you're going to do a check. If you don't do a check, and the instructions say to do a check, you're going to lose some points. Okay, so how do you do a check? You go back to the original 3. Always go back to the original. It's like a rumor. If somebody passes a rumor about you, you don't ask the last person. You figure out where the rumor started. You go back to there. You backtrack. You go back to the rumor and say, hey, what's up, bro? I mean, why are you saying this about me? Right? It's the same thing with a check. You go back to the originals, and you put the numbers in, and that's what you do. Okay, and each of them should check out. And then the final step is you write the solution. And the solution is, in this case, an ordered triple. And alphabetical order, you put the x, the y, the z. And that's how it's going to look. And you put parentheses here because it's a point, and you put the set brackets because it's a set. Okay? All right, so that takes care of that topic. And let's see what I got here. Okay, we're going to cover that next time. We're going to come and do matrices next time. But what you should be doing is let's see if I can find it. Homework, okay. Matrices, classwork. Okay, if you go on Blackboard, there will be, here's what we just did, I believe. This is the one that we just did. Yes, this is the one that we just did. Okay, so you're going to go back, and there should be someplace I listed homework. I'm not sure if I'm finding it now. This is an algebraic problem. All right, so this is on, oh, that's not it. Let's see. If you go on Blackboard, this should be on Blackboard. There will be some problems for you to work out. They're labeled classwork. Some are 2 by 2. Well, you can find them. I know that they're up there. Okay, so you go onto Blackboard, and you'll have problems to work out. And next time we'll come back and we'll do some matrices. Okay, have a good evening.